Yo, guys, we got GPU neural network training. It's working. Hype from scratch, from nothing, right? And I just wanted to talk about how this is working, how like the the current code for that looks. Maybe give a little bit of an architecture overview, because it took a lot of iteration to get to this point. A lot of this iteration was done off stream, and so I feel like it's worth just kind of talking about like start to end. What it looks like to train a neural network on GPU with no dependencies except for OpenCL. Yeah, so we have started with we have this goal of training a barcode scanner because I think that's like kind of like a fun neural networky topic, simple enough that we can do it, hard enough that we don't really want to do it ourselves. Although it's very possible, we just gave up. But before we get there, we've been playing around with the idea of neural network training at all, and we've started with the world's simplest problem to get there. Two inputs, A, B. These go to one output, and this output returns 1 if big, 0, or 1 if A is bigger than B, 0 if B is bigger than A. That's kind of like the goal. It's like the simplest problem we could think of, and we wanted to like experiment, make sure that we could get a computer to learn this before we move on to something more complex. The way that these neural networks are set up, right, is that you basically do a bunch of multiply adds with some thresholding. So in this scenario, you're going to have, A times some weight plus B times some weight plus some bias is going to determine some number. This is going to be some arbitrary number between, negative infinity and infinity, right? If you want this thing to be between 0 and 1, you might do something like huck it through some activation function that maps all numbers from 0 to 1. So one that kind of fits nicely in my brain, at right now is sigmoid, is that they call it, and it basically looks like this, where like small number, like really large negative numbers trend towards 0. This is kind of like it's kind of like this, I guess. So really small negative numbers go to 0, really big positive numbers go to 1, and anything in the middle kind of gets like a nice little S-curve in between. Okay, so simple. So we go sigmoid on this guy. Whoop, whoop, whoop. Okay, this maps these inputs to a number 0 to 1. And so the goal of our training is to learn these two parameters and this parameter. Now, we could make these up by hand, right? We have an expectation of what this is going to be. If you want to get a really big negative number when B is bigger and a really big positive number when A is bigger, you can basically have weight 1 is equal to negative weight 2 and make these guys big, is kind of the answer we're looking for. Okay? So how do we do this? Well, we've done an iteration already where we kind of trained this on CPU, tracking each number independently. So the idea here is you write down all of the operations you do, right? So we have, if we look at this formula, we have A times weight 1. And we can kind of like build a little graph out of these things and say this is a multiplication. And we have B times weight 2. That's another multiplication. We've got take these guys and add them together with the bias. So we have, bias over here, and we add this to that. And then we pass this guy through the sigmoid function, and that's it. This is our computation graph. Now, once we run this graph, we might want to know how wrong were we, right? So we compute a loss and we say, how incorrect were we? So basically, if we expected 1 and we got 0, the loss is big. If we expected 1 and we got 1, the loss is small. And the goal is to make this number small, right? We want this number to be small. And so what we can do is we can do a little bit of calculus and basically say, okay, if my loss is big, 1.0, what like makes up that loss? Like, how does weight 1 and weight 2 contribute to that loss? And it turns out that if you just kind of like take the derivative of these guys at each point and kind of like walk it backwards, so like say hand wavy, say you're taking like the derivative of a parabola, right? The derivative of x squared is 2x. You kind of bring like the power down here. Don't ask me why. It's just like a rule from calculus that I remember from when I took it 10 years ago. And if, x comes from something else, right? So say x comes from some other formula, 2x. Basically any individual change in this x is gonna like be be magnified by 2. And so it turns out that if you kind of like walk derivatives backwards like this and say like, I know this derivative, I know this derivative, I know this derivative, if you just multiply them all together, it turns out that like when you get to the weight 1 derivative times this derivative times this derivative times this derivative times this, you kind of get to like how much a change in this contributes to a change in this, and you can kind of just nudge this thing that way to make this number smaller, right? So you can go like, oh, I know that if I move this number by like a little bit or by 1, if I change this number, it will have this corresponding effect on the loss, and you just make those changes. And you iteratively do that because like, you don't actually have like a nice formula. You kind of have like some like wiggly thing. Probably, we're kind of hoping it looks kind of like something like this, where there's like a lot of wiggles, but it kind of like ends at some, semi-correct point. And you kind of just say like, okay, here I want to go this way. If I'm over here, I want to go this way. And hopefully over time you kind of trend towards the bottom of the bucket. Okay, so that's neural network training. Now, tracking this computation graph, shit. Doing this on CPU, shit. Let's not do any of that. Fuck that shit. We want to go fast. Vroom, vroom, vroom. We want to use GPUs and do as much fucking work as possible. And so that's kind of where we're starting. There is this specification, we can say. Also, you could call it a library called OpenCL. This is like Kronos are the guys who are in charge of like OpenGL, Vulkan. These guys have a bunch of like specifications for like things that you can run on many platforms, I guess, right? And OpenCL is an attempt at basically being like a CUDA competitor that can run on anyone, right? So this guy, he kind of had like a nice like level of abstraction for GPU compute. You can compile like what are essentially C programs that will run massively parallel, and you have like kind of nice CPU side control of, let me like take this stuff, put it in a queue of stuff that will run on the GPU, let me know when it's done, and let me like manage some memory in some way. That's kind of what this guy's providing for us. And so this guy is kind of at the bottom level of our abstraction here. We have OpenCL exposed to us as a C library, and in him he's got like a few concepts. One is, the base. I think the first thing we should think about is a kernel, which is the name for a thing that runs a lot of times at once, right? So if we can like look at maybe our add assign kernel. This is very simple. We write like a kernel, a C function, right, with like C style macros to annotate functions. This thing, we say, hey, this is a C function. We are going to have pointers to some chunks of memory. They are kind of in global space. We can kind of talk about that a bit later, but basically like these are things that are, this is memory that is accessible from anyone executing this thing. And the OpenCL infrastructure, when I call this, I'll say, hey, I have an array of 1,000 A's and 1,000 B's. Can you call this function 1,000 times? And on each iteration of this function, we can ask OpenCL. We can say, hey, what number am I? My version of this guy. And he'll be like, okay, I'll give you a number from 1 to 1,000. I'm running 1,000 of you at once. And all we have to do is say, okay, I will do my little plus equals from A to B, or from B to A, I guess, is maybe the right way to say this, and only handle this one element in that array. You can get like arbitrarily complex with these things, so we kind of spent a lot of time looking at this matrix multiplication. So given box of numbers 1, can we look at like matrix multiplication? Wikipedia. Hold on. Sir, I would like to go to the internet, please. Yeah, so given like 2 boxes of numbers, we're doing like basically multiply adds for each element in a row in A by each element in a column in B, and they go to some output. So like for something like this, we started thinking about like parallel summing, trying to like use many cores to do the addition segment of this thing. Not really important, it turns out, because if you do a slow version of this thing where you use each core to do a bunch of serial multiply adds. It's lower, like higher latency than the parallel version, but if you can just send more data at it, and then you're kind of fine. But anyways, so like for an example like this, we run our matrix multiplication once per output cell here, and each output cell calculation is in charge of doing like B1 times A1, B2 times A2, and adding together, right? So it's really not that crazy. We have like once again a global ID, which is like one of our outputs. We determine which row and column we're coming from. We like index from A within that row and B within that column, iterating, matching up A1 and B1, A2 and B2, etc., etc., etc. And then we just assign to some output. Huge. Okay, so this is the OpenCL kernel. Where is our picture? We need to keep track of where we are. Maybe we lost it. Maybe we lost it. So we have OpenCL, CL. Jesus Christ! Wait. OpenCL, and in here we have a kernel. Now, related to this guy, maybe we should use a slightly smaller. Hold on, I wanna make sure this is legible because it's gonna get kind of crazy. Actually, here we go. We'll take this one. Okay. OpenCL kernel. Now these kernels come from programs, right? So we have multiple kernels within a program. So OpenCL also has this idea of a program, and every time you launch an OpenCL program, at least in like our application, it's going to look at this like C source code and compile it into something that can run on your specific GPU. So depending on like what your GPU driver is, what platform you're on, right? Am I AMD? Am I NVIDIA? Which like series of cards do I have? The instructions that will be generated by this thing will be like a little bit different. And the third concept that we have is a queue. I'm just going to write the letter Q here so I don't have to write the whole word. But the idea here is that because like normally if you execute stuff on the CPU, you just kind of say like go, and then like your CPU is spinning and then you can just like do the next thing. When you're doing like GPU execution, it's almost like you're sending like a network request to the GPU and saying, hey, can you do this? And then like while you're doing that, I'll go do something else, right? And so the idea here is like network request is wrong, right? It's a PCI, but whatever. So the idea here is that like you take your kernel and you say, hey, I'm gonna like queue this up to execute, and I'll put him on some queue. And when this queue when it's done, he will respond with some like event. So that's another thing that we have to keep track of, events. EV for event. And I can like pull this event to see when it's done, which is like useful if you're doing things like uploading memory. So the idea here, the thing to remember here is we have a queue of things that will operate. You can do like out of order queues, but our queue in our version of this thing is just serial. So everything that we queue up will happen in order. But you could get really fancy with like out of order execution and event tracking. And the last thing that we need to write down is buffer or memory. So this kernel has to execute on some data. We need somewhere to put that data, and we need like a handle to like GPU memory that is holding this guy. Right, so your GPU, you buy it, on the box it says 24 gigs of VRAM. That's kind of how you can think of this stuff. So this is kind of like the stuff we have to work with. Now this is like a C library and has like constraints that we don't necessarily want to keep track of. So we kind of put all of this in a box over here, and we have a slight little wrapper to it is where we ended up. So we have our, our wrapper on top. We'll call this CL, maybe CL wrapper. And his job is to basically just be really, really low level, like almost one-to-one mappings of anything that we're going to use from OpenCL in our application, right? So this isn't like a generic wrapper library to convert C to Zig. This is kind of like we are using this thing in our environment, in our neural network training. Anything that we need to do that, this guy abstracts, right? So he's going to basically re-implement all of these types, but with the extra constraint here that we keep track of all these things in pools. So basically, I didn't want to have to make sure that every time I do literally anything, I have to remember to free that chunk of memory. Because, like, for example, if you allocate like an OpenCL memory buffer, right? This is a resource that lives on the GPU, and the kernel needs to know when it can ask the GPU to free that resource, right? So in your classic C style, every single buffer that you allocate is going to be something that needs to be freed, and if you don't, that's a memory leak. Ew. But when we're trying to stack on like lots of mathematical operations for neural network training, we're going to end up with like series of things, and I don't want to have to keep track of every single one of them because that will start to get unruly very quickly. So what we do is we added this concept of like a CL allocator, who basically his job is to kind of hold each of these guys, right? So he holds all of the kernels we've allocated, all of the memory we've allocated, all of the programs we've allocated, right? He keeps track of all this stuff for us. All the events we've allocated as well. The queue, not really so much. And what we can do is we can say every once in a while, just nuke everything that happened recently, right? So this CL wrapper basically says like, if I have like create kernel, make a kernel, he's going to call into this guy, create a kernel, and then put him in an allocator, which is kind of nice. Kind of nice for us. Yeah, nothing too crazy here. So far we have the ability to make buffers, run kernels, but keeping track of all that stuff is painful, right? So like a kernel, like we said earlier, this is like a thing that has been compiled for our specific GPU. So on app initialization, you like make your OpenCL context, you create your kernel, and that needs to like live somewhere. And every time you want to do math, any math, where you have like a kernel that you've written to do add assign, or is this in some CL? So like this thing where we've done add assign, this is like a kernel that needs to live somewhere. And I don't want to have to like carry these kernels around everywhere and think about them. I want to just be able to be like, GPU, do some math for me, please, right? So on top of this chunk of shit, we enter a new abstraction. A new abstraction. Whoa, wait, hold on. Let's kind of put this stuff over here. Boom. New abstraction. Math. Math. We actually call this a math executor. Executor. And his job is he keeps a reference to this guy, this OpenCL abstraction that we've written. And he holds a bunch of kernels, right? So he says all of the kernels we have to do for any math, let's hold on to these guys. Jeez, I wish my scroll wheel wasn't broken. So, we have an add kernel, we have like a matrix multiplication kernel, a sigmoid kernel, an add splat kernel, which like adds adds all numbers in a list to all rows of numbers in another list. We've got greater than, we got squared error, we got multiply by a scalar, right? All of these kernels, he holds all of these and gives us like nice little functions that we can run. That's just like, hey, math. Could we multiply this scalar and put your output on some allocator and multiply A by B? And he does all this stuff to like kind of finagle the arguments that we have in CPU side, like my buffer handles and like how many dimensions of these things are this like buffer represents. Like what are the dimensions of this chunk of numbers? It's like, oh, this 100 numbers is actually an array that's 2 by 2 by 25. Yeah, like if a 3D box of numbers, something like that, right? So he's basically sitting there in charge of all this stuff, which is great. Now we can do things like we can like do a matrix multiplications. And that kind of gives us everything that we need in order to execute a neural network, right? So back to our other example, of A, B, comes into an output that is, 1 if A is greater, 0 if B is greater. You can like you can represent any sort of like neural network. We should say your typical like layers, you can represent them as blocks of numbers. So let's get a little more complicated. You might see an example online where you have like, some inputs, and then these inputs go into like hidden layers, they call them, right? So you have like a couple layers of numbers. This is like the more complex version of this thing. And for each thing in here, you kind of like do these like multiplies by everybody before him, right? So this guy connects to him, him. This guy connects to him, him. This guy connects to him, him. And you get like this like nest of shit. But that means like for every single node in like this layer, you have to talk to every single node in this layer, right? And multiply by some weight. And so what's like a convenient way to represent that is you have like output numbers by times input numbers, weights, and you can kind of just put those in a box that are like out by in, right? So, at each spot in this box, this is kind of like how the first element in the output should be multiplied by each of the elements in the input, and you do this over and over again, right? Where are we going with this? Right, so for this problem, we can represent all of our multipliers in these boxes. So we have, in our shitty example, it's literally like weight 1, weight 2. This is our box. And we can do matrix multiplication with a batch of inputs, right? So we can say A1, B1, A2, B2, A3, B3. And when we do this multiplication, we're going to end up basically with an output set of, 1, 0, 1, for example, if this is supposed to, if A is bigger, B is bigger, A is bigger. We have our math executor can also execute like the sigmoid function that we need to like turn these into numbers. So this is actually going to turn into like, more realistically, these turn into big ass numbers, right? So like some big ass, 9999, negative 99999999, right? And then we put these through a sigmoid function, which says for each of these numbers, can we do that, right? So our math executor also has that. We have everything that we need. Everything that we need. But if we want to train our neural network, that is not good enough. That's not good enough, because once we execute all of the stuff that we need to get to this answer, we need to be able to say, how do I adjust these numbers in this box over here to push the error down, to make like the number more correct? And so enter new abstraction. New abstraction that sits on top of all of this shit. Gotta move this down. We got, let's make sure everything's still in line. Yep. We have tracing executor. Tracing executor. So this guy, he basically wraps the guy who does math, right? But he tacks on one more piece of information here. The extra piece that he tacks on is what the fuck did I do? So if we look at code here, basically all this guy owns is he has like our math executor, hype, and a node graph. And this node graph just says, let me hold on to elements that say, what was the thing that I was operating on, and how did I get here? So like, for example, if we were to do matrix multiplication, we write down in the node in our node graph, hey, this buffer came from a matrix multiplication of these two other nodes. And so what that allows us to build with this like very simple setup is we basically build that same graph that we were looking at CPU side, where it looks a little different now, where we have matmul. So we have like input as one big matrix, right? This is A, B, A, B, A, B. So this is our like input to our thing. This guy goes through a matrix multiplication with some weights. So we have weights, weight 1, weight 2. these guys go together into a multiply or a matmul like this. Then this goes through activation, so sigmoid, and then loss, right? So for any, and we can do this for like, a million numbers or a million pairs of numbers at once. It just follows this same graph. It's like this many operations. So, our graph keeps track of, he assigns each of these guys an ID, right? So 0, 1, 2, 3, 4. And then all he does is when he calls the underlying actual implementation, right? So if we call matrix multiplication here, all he does is he says, hey, I have some inputs here that are back, like that you've given me a thing that has like some node IDs, I guess, right? So we have node ID A and node ID B. Give me like the underlying versions of these things. Do that matrix multiplication, and then write down that this is where that matrix multiplication came from, and shove that into my node graph. Easy peasy. Easy peasy. And so every single function here just looks like that, right? Append node inner sigmoid. Append node. Oh, this is not a like math function, right? So like greater than, append node inner greater than, squared error, append node inner squared error, hype, right? Simple, really. And so all we have to do now is, once we have that graph of things, eventually we're going to want to come back here to like our neural network weights and kind of like nudge them in some direction, right? So it turns out that with like this structure, it's pretty easy to just mirror this graph, right? So this graph is just like a list of nodes, right? And we can just mirror this graph as for gradients as well. So we can kind of track the amount that each of these guys has an effect on the loss. And so we can kind of say like gradients is the same structure. Just instead of holding like the actual values in there, we hold how much of an effect they have on some number, right? So in main, on each iteration of our training loop, we say, hey, let's get some gradients out of this thing, right? And we'll just say, hey, this like tracing executor that we're using, can you backpropagate? Can you generate me a graph of how every single thing that made us get to this like loss number? Can you give me a graph of how all of those, how any change to any of the things in that graph would affect that thing, right? So we'll get something that's like weight grad will have in grad, which is not very useful to us right now, but we still compute it because we don't have any tracking of like stuff we care about. And then we'll have matmul grad here and like sigmoid grad here. It follows like the exact same shape, right? And all we have to do to get there is a little bit of like walking backwards of the graph. This part's like probably the trickiest part of the whole thing. But the idea here is that for each operation that we do, i.e. like sigmoid, or maybe squared error is a better example, right? So we have a kernel that implements the squared error of A to B. So here we have, diff is A minus B, and the output is the square of that thing, right? Easy. We also have like another operation that's like, what are the gradients of this thing? So we say, hey, how much does each element in this squared error affect the final incorrectness value? What were our inputs to this squared error function? And these are my outputs now. And all we do here is, in this function, it's A minus B squared. The derivative of this is you do power rule, take this down, so it's 2A minus B, right? Easy. And so then the trick here is how does a change in A affect this output, and how does a change in B affect this output? Well, any change in A directly moves this like 1 to 1. So the derivative here is 2 times the diff, where d diff equals A minus B. You get 2D here, and A changes D 1 to 1, so we're good. And B changes D in the opposite direction, right? So if you're looking for the difference here, a negative change in B will make it bigger, and a positive change in B will make it smaller. So you just do that thing. You take the 2 times diff, you multiply by downstream for chain rule, and then your outputs, you just put 1 positive, 1 negative. Hype. Right? So for every single operation that we do, we have the derivative function to go with it. And so all we have to do when we walk this graph backwards, wherever the fuck that was, right? When we were walking this graph backwards to create the gradients, all we have to do is call like our, if we were a squared error, we say, hey, can you call the backwards the gradient function for this, and then I'll write that down somewhere. Which is pretty hype. So this guy kind of generates, I guess on this graph, this guy generates gradients. Grads. Okay, cool. So here's the picture so far, right? We have OpenCL down here. He's got a bunch of he's got kernels, programs, a queue, some memory. We have like a couple abstractions on top of that kind of just minimally wrap that stuff, followed by a thing that can do math and a thing that traces the math. Easy, easy. That thing that traces the math can output gradients. So the last piece of this is once we have those gradients, we want to nudge those initial weights, right? We want to change our answer so that next time we run this, we're more correct. And so we have one more piece here. One more piece. Optimizer. So this guy, basically, for everything that we care about, so here we have this layer that holds our weights, essentially. That's his job. I guess, yeah, we have a layer. So this guy holds weights. And he holds weights as tracing executor tensors, right? So this guy has tensors, boom, which kind of reference these guys' tensors, underlying tensors. Hold on. My fucking scroll wheel's freaking out. So he references the underlying tensors, and then the layer can execute in a way where he can choose if he wants to be using the tracing executor or the non-tracing executor. He can kind of switch between them, which is kind of nice. So that way, if we are training, we use the tracing one, but if we're just running the network, we don't need all this extra tracking overhead, so we just don't use it. So he references one of these tensors over here, or many of them maybe, right? For his weights and biases or whatever. And all we do is anything that we care about, we feed to the optimizer, right? So the optimizer will have also lists of tensors that he cares about. And he can kind of identify them by ID, which is really nice because what we do is we feed the optimizer. I should fucking, let me move this optimizer over here. It's better if he's on the left here, I think. Oh my God. It's better if he's over here. So he has a list of tensors that he cares about. And he also has the list of equivalent gradients for those things. And all he does is he says, for each tensor that I care about, every once in a while, for each tensor that I care about, can you just look up the gradients from this iteration, that are how much each of these things contributes to how wrong we were? Can you just, oopsie, is what I have to do. Can you grab that guy from the gradients? Can we get the original value that we care about? And can you just slightly modify that thing? So we multiply this thing by some learning rate. We invert the learning rate because we're trying to get this thing to a smaller number. We take the gradient for that thing and we just add a sign. Huge. And that's all the optimizer does. I think this is called stochastic gradient descent. I don't know. It's just nudge, please. Nudge everything equally. All the numbers that we care about, just nudge them. There are better rules for this, but for now, this is our optimizer. And that's kind of the whole shebang. Now, looking at the main loop a little bit, for this training of this thing, all we have to do is we create a batch of numbers. We do this on the CPU. We could do this on GPU, but I didn't want to implement PRNGs on GPU right now because we won't need them later, so there's no point. So we generate some numbers on the CPU. We upload them to the GPU. We execute our neural network on those things. we get the answers back. We look at them on CPU just so that we can like log them a little bit, like check how correct we are. But then like on GPU, we do, you know, we calculate how wrong everything was. And then all we have to do is backpropagate and optimize, which is pretty hype. Now, on each iteration, what's kind of nice about like this allocator type that we made down here is we can kind of like, this thing is just like a linear allocator, essentially. He's got kind of like a list of all of the things in order-ish that we allocated from OpenCL, right? OpenCL stuff. And so on each iteration of the loop, all we do is like write down how much stuff had we allocated when the loop started, and just like fucking nuke all of this stuff, right? So we've kind of like created our own like simple garbage collector, right? So within one iteration of training, we kind of just go buck wild with allocations. We don't care. We leak everything. Everything just like falls, goes wherever. We never try to free individual things. And then on each iteration of the loop, all we have to do is like restore these like pieces of state that have changed to like where they were at the start. So, our tracing executor, he's got like a graph of things. We just kind of reset the graph to where he was at the start. We got, OpenCL allocations. That's like a list of things. We just reset that stuff back to where it was at the start. Same with like heap allocations, which is pretty nice. So overall, this stuff is working pretty well. I guess we should do like an example training, right? So here's an example of us just ripping through batches of 1,000. We can rip through way bigger batches, right? If I say do like 1,000,000 at a time, 1, 2, 3, 4, 5, we can, oh, hold on. I need to up initial memory allocations to make this work, I think. Because some stuff on CPU doesn't work. But yeah, here you can see us like ripping through stuff. You can see that the numbers are kind of getting like more wrong. This is because our learning rate, our like incorrectness number is scaled to how many elements there are, right? So we're probably just we're trying to push everything too hard, and it's kind of just like flip-flopping between incorrect numbers. But if we reduce the learning rate a little bit, by a factor of 1,000, I think that this should kind of work again. So here you can see now he's kind of getting to something like approximately correct. Not perfect, but pretty good. Pretty good. And you can see like this number, we're doing like 1,000,000 of these at once, and this is just kind of flying. So this is way, 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 way faster than it could go on CPU, like way faster. So kind of big win there. We also have proof here. If I look at my GPU's kind of resource usage, that we are in fact doing stuff. We're only about like 60% utilization. I don't know if we could probably get that better. Our like RAM usage is pretty low. We could crank this up. We could do way more stuff at once than we're doing right now. And then I hit Control C here, and these numbers should drop. Yeah, so pretty hype. Pretty hype. Happy with that. I think that this kind of like set of stuff is feeling pretty good. I think this is like an architecture that works. It's nice to be able to trade out tracing and non-tracing versions of this thing. This makes like a little bit of API overhead on this guy, which is like a little bit suboptimal, but fine. And yeah, neural network training, not that bad. Not that bad, man. So yeah, I think I'll post a link to this commit in the description if you want to take a look. It's just the third commit in the smelly repo, Spheriphoria's MLE repository. And you can take a look. But otherwise, I think that's all I got to talk about. Thanks for tuning in. We'll be back at this tomorrow. We're gonna go live tomorrow and work on getting some barcodes training data set up so that we can actually like do something, work towards training a barcode scanner. That's kind of the next step, but we'll see. All right, cool. Peace out.